Calculus was developed in the latter half of the 17th century by two mathematicians, Gottfried Leibniz and Isaac Newton. Newton first developed calculus and applied it directly to the understanding of physical systems. In calculus, calculus uses operations that employ functions and integrals to calculate the rates of change, and the two categories of calculus are called differential calculus and integral calculus. With the existence of the calculus, it can be used and applied especially in our everyday life in a wide range of fields such as engineering, medicine, business, physics, biology, research, analytics, and so on. In this video, between the two of the fields that we are going to touch on is that in the aspect of engineering and physics, and how the calculus are going to apply into these two different fields. Suspension bridges are among the most commonly built bridges in the world. Such bridges feature long horizontal decks which are hung below suspension cables on vertical rods or hangers. Assuming a negligible weight as compared to that of the deck and the vehicles being supported, the main cables of a suspension bridge will take the shapes of parabolas. Calculus enables us to determine the shape of the bridge cable when the total weight of the load, the cable, and the roadway per horizontal foot is constant. The cable is assumed to be perfectly flexible and is inelastic. Both properties are proposed by a piece of ordinary rope. There are three forces acting on AP: the horizontal pull T0 to the left, the downward pull Wx of the total load, and the tension or pull T tangential at P. Because the arc AP is at rest or in equilibrium, the three forces must somehow offset one another. For if there was some net force, the cable would move or bend under the action of that force. Alternatively, we may say that the horizontal forces must offset one another and that vertical forces must do likewise. The tension T is equivalent to a horizontal and a vertical force acting simultaneously. For a tension is a force, and any force may be replaced by the proper horizontal and vertical components. Specifically, the tension of the magnitude T is equivalent to the combined action of the horizontal component T cosine and the vertical component T sine. The horizontal component T cosine must be offset by the only other horizontal force that is acting, namely T0. The vertical component T sine of the tension must offset the only other vertical force that is acting, namely Wx. If we divide 2 by 1, we obtain. Now tangent is the slope of the tangent line at P, and this slope is y prime, where y prime is the derivative of whatever function represents the shape of the cable. Thus, by anti-differentiation, we obtain. To fix the constant C, we can choose the x-axis so as to pass through the point A of the main figure. Then y is equal to 0 when x is equal to 0, so that C is equal to 0. Let us note one or two implications of the result 6. Although the equation seems to involve two unknown quantities W and T0, only their ratio is involved. We can in fact write the equation as y is equal to kx squared, where k is equal to w divided by 2t0. To determine the equation of the parabola, we need to know the coordinates of one point through which the parabola must go. Suppose that we do specify the coordinates of one point, say the point 2, 3. Because the curve is symmetric with respect to the y-axis, the point -2, 3 must also be on the curve. Moreover, the lowest point on the cable must be the origin if 6 is presupposed. Hence, to specify the coordinates of one point means really that the width from -2, 3 to +2, 3 and the depth 3 are specified. We know, however, that the cable must have an equation of the form which is y is equal to kx squared, and there is only one parabola of this form through a given point. Hence, it would seem that if we fix one point, that is, fix the width and the depth, then there is no freedom to choose the load that the cable will support. However, this is not true. The quantity K is equal to W divided by 2T0. So fixing K fixes only the region of W to T0. If we increase W, the load per horizontal foot, then T0 must also increase in the same ratio. To sum it up, if the width of a cable and the depth at that width are specified, there is only one shape for the cable regardless of the load, provided that the load is constant over each horizontal foot. In the world of physics, there are tons of formulaic and mathematic formula in it. Besides, the applications of calculus in physics are abundant. This is because time is virtually always a factor in physics, and because modeling change is the primary function of calculus. The applications include all matter of kinematics, electrodynamics, fluid dynamics, and more. So let's take a look at a basic example of calculus in kinematics using go-karts. You're driving a high-speed go-kart, racing your friend. When you cross the finish line in the first place, you hit the brakes and decelerate constantly at 16 feet per second squared. Your go-kart travels 200 feet after you hit the brakes before it finally stops. How fast were you going when you first brake? In this case, there are three functions that are related, which is acceleration, velocity, and position. After defining these three functions, we get st, which represents position, vt, which represents velocity, at, which represents acceleration. Since we know the acceleration function at is equal to negative 16, that we are decelerating, so the acceleration is negative. We can take the antiderivative to find the velocity function vt. Now let's take the antiderivative of our velocity function to get our position function. If we consider that at time t is equal to 0, the position is 0, we can see that the constant d is equal to 0. This leaves us with the following functions for position and velocity. Now let's solve for n, which is the time it takes to come to a complete stop. We will do this by plugging n into our equation for our time value and using substitution with these two equations. From here, it's very simple to plug n into our other highlighted equation for c to reach our final answer. It took 5 seconds to stop, and our go-kart was originally going 80 feet per second. Also, as complicated as this calculation may seem, it's actually very basic. So this is how the calculus are applied in the field of physics. Imagine if we're living in a world without calculus, what would actually be happen in that case? Without calculus, we wouldn't have cell phones, computers, microwave ovens, radio, or television, all because these items require calculus in order to be invented. Same goes to the two examples that has been explained. We could have get into some technical accidents such as the inability and dysfunctioning in the brake of go-kart, and probably the bridge wouldn't be that stable or safer for the citizens to pass by. This shown how important it is to have calculus and play a crucial role in our life. In a nutshell, calculus, like other forms of mathematics, is much more than a language. It's also an incredibly powerful system of reasoning. It lets us transform one equation into another by performing various symbolic operations on them, operations subject to certain rules. Those rules are deeply rooted in logic, so even though it might seem like we're just shuffling symbols around, we're actually constructing long chains of logical inference. And lastly, it makes a huge impact in the world of many different aspects, not excluding our everyday life. Thank you.